It's a pleasure to be here today to talk to you and give you, I guess, a bit of an insight into our Croda partnership that we have ongoing with the University of Nottingham and York. And a real pleasure to be talking alongside Steve Howell as well. So I actually did my PhD in Steve's group, so it's great to be back together united on stage here. So, our prosperity partnership is focused on polymers in liquid formulation, and what we'll touch on today is probably some topics that have already been alluded to earlier in our session this morning, especially from Charlotte as well. When we look at new polymers, we need to think of the structure, because we have to target the properties that we know our existing heritage technologies offer. Biodegradability is key in introducing this into our polymer backbones. And performance is essential. We have to ensure we maintain the same performance in order to have a positioning in the future for the sustainable and biodegradable offerings that we want to provide. So this partnership, we're really trying to lay the foundation for new technology platforms for the future. So it's quite a step change in the way we're thinking as a business. Sustainability and biodegradability, they're a topic of increasing importance. You hear a lot about biodegradability requirements from customers, from consumers. We're in a changing regulatory landscape, so this is really influencing the choice that customers want. And finally, for Croda, this journey really aligns with our own ambitions for net zero. We can't achieve our targets if we continue to innovate from our existing platforms. So we have to change, we have to have a step change in the way we think, and it has to start now. Biodegradability, I know Andreas and Chris will discuss this in the next two talks in further detail, but it is a very interesting and challenging and complex topic. Because when you talk about biodegradability, the definition varies depending on your sector. You've got a very set number of methodologies that you can work within, and there's certain gold standards that we target that are interwoven into regulatory framework. However, how relevant they are to an end-of-life fate for a polymer aren't necessarily aligned. And finally, when we talk about biodegradability, a lot of these test methods are very time-consuming, like 28 days for an OECD 301 methodology. That's a long time in your innovation pipeline cycle to get a response on what choices you want to make to change the architecture to either improve or enhance the biodegradability functionality. So there are certain limitations in the innovation area here. Just to set the scene on what Croda are trying to achieve with this prosperity partnership is look for new chemistries that provide the effects of the synthetic polymers that we have within our portfolio today, but with that biodegradability and inherent sustainability. We currently achieve this using acrylic-based chemistries and our oxalates ultimately. So that's our performance targets quite clearly spelled out. If we look at where these polymers are used for us and our customers, it can be film forming applications. So they can be applied to seeds to help sowing seeds effectively in fields. They can be used to thicken a shampoo in personal care applications. They can be used to emulsify or solubilize fragrances, for example, or used in crop care to disperse particles. So the approaches that we can take is, number one, look at improving the biodegradability of existing platforms, so introducing biodegradability into polymers we know to form. Second approach is looking at polymer platforms that we know degrade and modifying them to improve their performance. Well, the third platform is really look completely outside. New technology, so we have to map that performance and biodegradability. So it's challenging, but this is where we can have the biggest impact. And this is the focus of our prosperity partnership. It's more risky, but we really wanted to leverage their expertise at the universities to help us achieve this ambition. So this was probably 3 years ago now when we had our interview for the Prosperity Partnership. We had Tom Farmer, who's now moved to Unilever. So we've had a little swap, seamlessly fitted in Antoine, who's joined at York as the lead PI. So we're really pleased to have his expertise join us within this collaboration. The overarching aim of our Prosperity Partnership is to launch or have the pipeline launch for 5 new products. And we know that's ambitious, but we want to have that kind of commercial driver at the end of this. All the work packages we have are interwoven. It is complex, but they're all interlinked. And we'll hopefully give you a little snapshot of each of these sections throughout this talk. So if we look at the monomers and building blocks, there's certain considerations we have to consider when we're redesigning the established technology platforms. We need to think about the sustainability of the building blocks we use. Functionality is key so that we can optimise the performance elements. And thirdly, that degradability is also essential, either via introducing degradable linkers, as well as considering that non-persistence of the building blocks that we're using as well. So we're taking 3 approaches. We're looking at commercially available bio-based materials, really so that we can build and understand that understanding of structure, performance, biodegradability in model systems and get up and running to build understanding earlier on. Work ongoing at the University of York is looking at novel lactone chemistry, introducing functionality in the ring structure that we can take advantage of when we do our ring opening polymerizations. And Nottingham are leading the work package on novel hydrophiles and hydrophones, where we're looking at renewable sources from coffee grounds, corn, we won't call it waste, material from the paper industry. So if we take a bit of a look at the polymerization approach, we're looking at ring opening polymerization and polycondensation. And with the ring opening polymerization, it really allows us that tight control of the end particles that we achieve. We can control the architecture, control the molecular weight, control the dispersity. When we look at polycondensation, it's a step growth polymerization, so we don't necessarily have that control of the molecular weight distribution, but it is probably a more true representation of the type of polymer distributions that we have in the current products. So we wanted to look at both in parallel. And I'll just give one snapshot on each chemistry set. But the work ongoing at York has been focused on looking at functionality you can typically achieve from polyacrylic acid type chemistry with the novel lactones instead from bio-based raw material, looking at controlling that molecular weight and functionality especially. And what we can see is some early, really interesting results. So this is water thickened with 1% of the novel polymer achieved from York. And you can see, turned upside down, it creates a clear gel, suspending bubbles. You know, that's really exciting initial results. So we're getting that performance element that we want. It also degrades, which is brilliant. However, in this case, it actually is too degradable. So within a month, that thickened structure is completely broken down because it is being hydrolytically degraded in that water phase. So we're having this challenge and this competing complex of we want it to be biodegradable, but not too degradable that it degrades in its use. So now a lot of the work is looking at re-engineering backwards. We have to make it less degradable so that we can maintain the performance for longer. Some of the work we've been doing with Steve Howell at Nottingham is looking at condensation polymerization. We've looked at controlled extension of hydrophilic head groups. This is where the research is going at the moment. Really controlling either the linearity or the degree of branching. And we're coupling this with a range of hydrophobic tails to give us that surface active properties. And again, we've got some really interesting, nice results. 1% in water, we get a very nice foam. We know that it's performing the way that we want. And we're now looking at this to build that understanding of structure, performance, biodegradability. Because it changes. When we tailor that architecture, vary the head group, vary the tail, we get very different biodegradability rates. So we're going to have to balance that with the performance that we want and see, ideally, are we able to marry them up? So that's where the work is going in this phase. We're in that loop of optimizing the biodegradability and the structure and the performance. Performance and degradability screening is also key, obviously, to this project. And I'll just touch very briefly on biodegradability to start with. I know they'll be discussed further in the next presentations. But this is just a quick representation of the sewage treatment. So where a lot of the polymers we use in personal care products will ultimately end up down the drain, they'll go via this multi-step process. When we measure our biodegradability using an OECD 301 test, it's in an aerobic environment, water, for 28 days. It's not representative at all of the realistic end-of-life fate. And in this case, we're not even touching on how if you spray something on crops, how it will enter the soil, how it will then migrate to the water. So these test methods aren't representative of what happens. So we still have to work within the framework, that the test methods that are there. They're probably the best thing we've got at the moment. So at Croda, we've introduced in-house testing, so we can evaluate polymers that are generated from this prosperity partnership. But we're also looking alongside York to develop capabilities in anaerobic digestion. And we can already see from our benchmarks how the degradability is significantly different depending on the environment and nature of those microbe species. Thirdly, accelerated testing. Can we shorten down that 28 days to weeks, days ideally, to give us an indication, at least on what would be a successful candidate at the end of the longer test methods? And I guess the fourth area is this legislative and dissemination piece, which, you know, we all agree that the current framework isn't fit for purpose, and the PLF task force and this group, these people, us today, it's a great forum to challenge this together so that we can implement and ideally drive change. Before handing over to Steve, I'll just quickly give you a bit of a snapshot on how we do the performance testing element. So we've got facilities and materials innovation factory at the University of Liverpool, and we've established quick screening methods to understand that structure performance relationship across film forming, rheology and surfactancy. And what's really great is that we can utilise the robotics, the automation and that advanced analytical equipment to ensure that this process can be run high throughput. So actually we can quite quickly get an understanding on the performance element of the new polymers generated. The bottleneck for us at the moment is the biodegradability testing because of those long timelines required to get your end result. I'll hand over to Steve, who'll give you a bit of a snapshot on our optimisation and scale-up.
Right, seamless handover. Okay, so thank you, Amy. So what we're doing is I guess we're using the talents that we have at our universities very well in the UK. You've already heard today from Charlotte and from Matthew about some of the things going across the UK. We're very good at this. And I think we have to make sure, as well as getting this government to recognise the importance of the chemicals industry and the problems that we face, I, as a university academic, am really feeling at the moment the fact that our government and our country doesn't recognise the value of universities. So I want to add to this argument today by telling you some of the things that we're doing that are really valuable. So in this final snapshot, I just want to show you some of the tools we're bringing to this project to help Croda to solve the problem of PLFs. So one thing we're doing is, with my colleague Jonathan Hurst, we're looking at machine learning and AI. And so far, there's been a little bit of work looking at chemistry using AI. It's coming along. There's not been very much at all using polymers, because polymers are just incredibly difficult to model and to teach a computer how to recognize a polymer. But it's coming. Slowly but surely it's coming. There was this paper in a journal in the USA recently that showed that you could start to describe structures, and this uses a sort of, it's called a stochastic nearest environment process. And this plot here shows degradation. So most of the polymers here, the purple ones, are not degradable. The yellow ones are degradable. And this grouping looked at 600 odd polymers of different structures and worked out how to tell the computer which ones were degradable and which ones were not. And what we've done is we've been building on what that American group did, and we've fed in another 20 or so polymers that we've made and shown the computer how to learn from that. So we're starting to move towards the holy grail where we might be able to actually predict degradation in advance. We're not there yet, but we're starting to move towards that. And that's really, really important. That's something that's going to help everybody. We're also looking at using biocatalysis. That's something that's been a common theme today. And it's something that's really, really important. Our colleagues at York are big experts in using enzymes to do processes. But here are two processes that are really quite difficult. The biovinegar approach normally requires using peroxy acids. Difficult to handle on a commercial scale, but they have figured out that you can use these monooxygenases to do some really nice oxygenation and produce some lactones that we can polymerize. And they're also working with these ene reductases. These are enzymes that enable you basically to add hydrogen. Hydrogenation is not an easy process to carry out on a commercial scale. We can do it, we do it, but if you could do it with enzymes at room temperature and room pressure, that would be really quite cool. So we're working on enzymes that can deliver that kind of new technology. And again, we're delivering some new lactones that could be really quite interesting, coming from feedstocks that we derived from nature. I'm at Nottingham. I'm also involved in green chemistry and sustainability. We actually have a carbon neutral building that's a test building and how to develop things that won't influence the environment or negatively. But I'm also involved in doing chemistry. And some of the things I've been looking at recently, as Amy said, are in polycondensation. So here's a polycondensation reaction we got interested in. Azelaic acid is something that you can derive very easy from nature. You can make it from oleic acid as well. And if you try and do a polycondensation reaction of that with a diol, it's actually quite difficult because that monomer, that acid monomer, melts at 110 degrees C. So you've got to hit it hard just to get it to start to melt. And if you want to do a polymerization where the reaction gets thicker and thicker as your molecular weight grows, then you need to go to 200 degrees C to make that reaction happen. That's okay, that's achievable. But once you start doing that, you're kicking in a lot of energy to make that reaction happen. And also, the polymer you're making is thermally sensitive. And then, you start to char it and break it down as you're making it. So that's really difficult. So the obvious thing a chemist would do is you'd put it in a solvent so you could do the reaction dilute. But if you find out that your azelaic acid doesn't dissolve in any non-polar solvents, you're a little bit stuffed. You can't put it in water because the reaction won't work in water. So this is really, really difficult. So I've spent most of my career working with CO2. And you've heard today from colleagues that CO2 is the bad boy. Everybody wants to get rid of CO2. But I've been using it quite positively to actually help to influence reactions. If you squeeze it, it becomes something called a supercritical fluid. It has properties that are like a liquid, and it makes things less viscous than they normally are. So we apply this to this reaction to lower the viscosity and to introduce melting of the monomer. And we found that we could do this reaction at 35 degrees C in the presence of CO2 at a high pressure. And you can squeeze the CO2 to give you this effect. So good was this that we could introduce an enzyme, because the enzyme can tolerate 35 degrees C, and it could allow us to build up this polymer at 35 degrees C. So massive energy saving and a lot cleaner system, and making positive use of the CO2, that's the bad boy. So I think there's some good things coming out of that we're trying to work on. The byproduct, of course, is water, and that can actually be taken away by the CO2 because there's some affinity with CO2. So we've done a little bit of work on scaling these things up. 1 litre is about the academic limit we can go to. I can't get a lot bigger than that, but we've done that and it works reasonably well. I and my team have been out and about. We've worked at different processes now at 100 litres, and this was at a pilot plant out in Austria. And we've shown that some of the things we're working on can be scaled. And I'd like to get to this kind of scale. These are real-sized people here. And this is a CO2 process out in Germany that decaffeinates coffee using high-pressure CO2. So you can scale and you can handle that kind of pressure, and you can do good stuff with it at the commercial scale. And I'd like to think that some of the chemistries we're developing could be taken to that kind of level in the future. So we've got lots of challenges to overcome in our projects. I'm delighted to be working alongside Amy again. We're doing some great things, but we've still got to figure out all of the structural flexibility that we need. We're creating novel monomers and polymers, and we've got to get the right level of flexibility in those structures that we're creating. We need to balance the stability against the biodegradability. Look, you know, Amy and a colleague have told me that we're going to have 5 new products on the shelf by the time this grant expires, which I'm delighted by. I want to be able to take my wife into the local Tesco's and point at the bottle of shampoo that I've made. That will be a big thing for me as an academic if I can do it. But I also want to know that that bottle of shampoo is going to last for 6 months. It's not going to degrade on the shelf, and the shampoo will still do its job. So we've got to get that challenge right. And in doing all of this, we've got to translate this research onto the industrial scale. And that's a big challenge for us because we're coming up with new ideas involving all the different things that I've mentioned to you. We've got to get those right. So this project, for me, it's really, really exciting. We are developing future technologies. We're coming up with the new ways of doing things. We've got a pipeline for 5 new products, and we're going to be influencing Croda's and others' pipelines for the next 10 to 20 years. We're generating new processes and new ways of doing things, and I think that if we can solve the biodegradability issues that we mentioned there, we're on to something that could be really quite powerful. And perhaps most importantly, we are developing the new people. We are developing fantastic new people who will be able to put all this into place, and that's something that's being not done just in Nottingham. You've heard earlier today, universities across the UK are doing this and doing it extremely well. And I'm sure universities in other countries are doing it just as well. So I think that we're doing great things, and I'm really excited about the future. Just to say thank you from the whole team here. This is our latest get-together. We've got everybody appointed now and in place, and I'm absolutely delighted by the level of commitment that Croda are showing and our colleagues at York and at Nottingham. And I think we're doing really good things. And just plug for Andrew as well. None of this would have happened without the PLFs, sustainable PLFs process, and Roy for leading all of this. It would not have happened. I cannot have imagined myself working in this area. I'm now doing things that involve companies like Croda and L'Oreal. In fact, one of my colleagues the other day said to me, Steve, why the hell are you working with people like L'Oreal? And I said, well, because I'm worth it.
Very grateful. Are there any questions from you, Bill? You know, I am always hungry for questions, so I will steal the show by I'm opening it up to the floor. But I have one. So you're 18 months on into your partnership, and clearly things are happening. But is there something that we can learn from this industry academic partnership? You know, like the best case study, as it were. I mean, can you give us some sort of tips as to how this partnership, other people can also learn from these sort of.
So I think from my perspective, it's a case of me putting my listening head on and listening to the problems that Croda actually have. So, you know, I've grown up in an environment as an academic where I want to tackle the world-leading problems. I want to do the most complicated science sometimes. Actually, sometimes it's the difficult things that maybe don't seem to be so difficult in terms of academic ability, but they're impractical, and we've got to find ways around them. So some of the stuff we're doing, you know, polycondensation polymerization is not very sexy, right? But we're doing some quite interesting stuff now to really change the way that polymerization is looked at, and maybe change it generationally in industry. And I'm fascinated that I'm able to contribute to that.
Oh, it's really very pleasing from our point of view. I guess from a Croda perspective, it's that realisation that we can't do this alone. You know, we have to go to the academics where the expertise lies to really together move towards that end goal, and also work together with other industry partners as well. You know, biodegradability goes beyond just Croda. That's a challenge for us all across industry, and it's looking at how we can kind of together try and change, I guess, the future for the better for PLFs. Please, Lord, yes. Remy, is it left? Yep.
I'll buy you a pint later, mate. Anyway, thank you. I just want to make a comment on this. And innovation in my world has 2 I's and 2 D's. The 2 I's are insights and ideas, and the 2 D's are dialogue and delivery. And the intent with much of what we all did together was to provide the forum for those 4 things to sort of be mixed around. Now, what we need to do is to create system change which allows that to happen more commonly in our world. And so that's the challenge to the RSC. And I was really encouraged to hear Charlotte talk about schema today, because I think that environment can allow that dialogue to happen more and more. And I'm going to encourage the industry partners in this room to consider what resource from a people, an in-kind, or indeed a financial point of view they can give to this kind of dialogue, this crystallizing center concept around change. Because only then will we get to sustainable PLFs 2040. So thanks. Honestly, it's great that you two are working together on this. Brilliant. Thanks very much.
Thank you, Roy. Thank you, Steve, and thank you, Amy. Once again, please may I welcome